All right, let's talk about properties of random matrices. So in my examples, x and y are random matrices. And what do I mean by that? So by a random matrix, I mean a matrix that consists of a random variable. And so this is in opposition to something like a constant, which would not be a random variable. So x and y are random matrices. A and b in these examples are constant matrices. All right, let's talk about expectation. So this is a big statistical term. We use this a lot. Expectation describes the average value. In math speak, we write it like this with this capital E and then brackets x. And so remember from probability that the expectation of x for a discrete random variable is going to be the sum over x times the probability mass function. And for continuous random variables, it's going to be the integral over the space of x times the distribution of x. So here are some expectation facts. The first is, if x and y are both random matrices, then the expectation of x plus y is equal to the expectation of x plus the expectation of y. So you can pull expectations through like this. You can split them when you're using addition. If A is a constant and x is a random matrix, then the expectation of A times x is equal to A times the expectation of x. So you can pull constants out when they're multiplied like this. Similarly, if you had both A and B as constant matrices and you took the expectation of A times x, a random matrix, times b, a constant, you could pull it out like this. So you have a in the front times the expectation of x times b. Okay, so I'm going to give you a couple minutes to try these. I want you to solve the following. Here, my little a is a constant and x and y are random matrices. All right, so the expectation of a times x, if a is a constant, regardless of if it's a matrix, so if it's just a constant number or a constant matrix, we can pull it out to the front like this. So we have a times the expectation of x. Similarly, if x and y, if they are random matrices, we can still pull the expectation through, so we can basically turn the expectation of x plus y to the expectation of x plus the expectation of y. Now the expectation of x times y, this was a trick question, but we actually cannot calculate this with just the information that I've given you. There are certain cases where you can split this out depending on things like independence, but if you're just given something like this, you really need to kind of do the long way to be able to calculate what this expectation is. It's not something that you can just use a rule to get. So we're going to leave that as a question mark for now. Okay, covariance. So covariance is a measure of joint variability between two random variables. And in math speak, we write it like this, usually with the abbreviation COV for covariance. And you take it between two random variables, for example, x and y. And so you'll maybe remember from probability that the covariance of x and y is equal to the expectation of x minus the expectation of x times y minus the expectation of y. So this is the definition of covariance. And here are some covariance facts. So again, x and y are random matrices, a and b are constant matrices, and little c and little d are constants. So the first fact is that the covariance of x and y is equal to the covariance of y transpose and x. The next fact is that the covariance of x plus c and y plus d is equal to the covariance of x and y plus the covariance of x and d plus the covariance of c and y plus the covariance of c and d. So basically we can distribute this through to pull out each of these four parts. Okay, so now we actually can reduce this down a little bit, and you might intuitively kind of see this, but remember that c and d are constants. So what's the covariance between a random variable and a constant? Well, covariance describes this variability between two variables, how two variables covary. And so it doesn't really make sense to have a covariance between a random variable and a constant. And in fact, the covariance between a random variable and a constant is going to be 0. And so what that means is that this covariance of x and d, covariance of c and y, and covariance of c and d are all going to be 0. And so the covariance of x plus c and y plus d is just equal to the covariance of x plus y. These constants, adding them in, doesn't actually change the covariance at all. So there's not an impact from these constants. All right, now what if we have this type of situation where instead of adding the constant, here we're multiplying our random variable x and y by these constant matrices. And so x is multiplied by the constant matrix A, and y is multiplied by the constant matrix B, and we'd like the covariance between AX and BY. Well, in this case, we can pull out these matrices. We can pull them to the outside of this covariance, and we end up with A times the covariance of x and y times B transpose. Okay, so those are some covariance facts. Let's try it. So what I want you to do is calculate the covariance of the following: of b times x and y, and of c and y. All right. So the covariance of bx and y is going to be b times the covariance of x and y, because b is just a constant matrix, so we can pull it out to the front. And the covariance of some constant c and y is going to be 0, because the covariance between a constant and a random variable is always going to be 0. All right, so variance measures the spread of a variable. In math speak, we write it like this, with VAR of x, for example. And you'll recall from probability that the variance of x is equal to the covariance of x and x, which is equal to the expectation of x squared minus the expectation of x squared. So in the first case, the expectation x squared is inside the expectation, and in the second case, the square is outside the expectation, and that's important because these two are not necessarily equal. The expectation of x squared is often not equal to the expectation of x with quantity squared. Okay, so again, x and y are random matrices, a and b are constant matrices, and c and d are constants. And so the variance of x plus some constant is going to just be the variance of x. And the variance of some matrix A times x is going to be equal to A times the variance of x times A transpose. And if xi's are independent, so if x's are independent, then the variance of the sum of the xi's is equal to the sum of the variances of the xi's. But if they are not independent, which is often the case, then you cannot do this, where you can basically pull the sum out. Okay, so what I want you to do now is I want you to show that the covariance of x and x is equal to the variance of x. And so you're going to use that definition of covariance that I showed a couple slides ago and show that that's equal to that definition of variance. I'm going to give you a couple minutes to work through that. All right, let's do it. So the definition of covariance is the expectation of the first thing we're in the covariance, so x minus the expectation of x, and then times the second part, x minus the expectation of x, since this time we're taking the covariance of two random variables that are the same, two random matrices, x and x. So this is just by definition what covariance is. So now I'm going to FOIL this inner part here. So I'm going to distribute so that I can further simplify. And so I end up with x squared minus 2x times the expectation of x plus the expectation of x squared. And using those expectation facts that we just learned, now let's pull this outer expectation through this. And so now we get the expectation of x squared minus 2 times the expectation of x times the expectation of x plus the expectation of x quantity squared. And so you'll notice this part here, expectation of x times the expectation of x, this is equal to the expectation of x quantity squared. And so I could replace that here and combine these two final terms and end up with the expectation of x squared minus the expectation of x quantity squared. And this is our definition of variance. So the covariance of x and x is equal to the variance of x. All right, the final piece that we're going to talk about is what it means to be unbiased. And so what does it mean for something to be unbiased? Well, if x is a statistic used to estimate a parameter theta, it's unbiased if the expectation of x is equal to theta. And so we're going to be using this in just a bit to show that the expectation of beta hat is equal to beta. Basically that our estimate of beta is unbiased.